Okay, good evening, everybody. I hope everyone's having a wonderful day. So, one thing before I get started, I just want to mention that in the next couple days, I'll be releasing the final assignment. So just keep an eye out for that. I'll make sure I put out an announcement when that comes out. But anyways, today we're going to be talking more about AVL trees. So remember last day at the end of class, I defined what an AVL tree is. It is simply a binary search tree that satisfies the so-called height balance property. So remember, the height balance property is that for every one of the internal nodes, that if I look at the left subtree and the right subtree, and if I look at those nodes' heights, they are only allowed to differ by at most 1. So this has to be true for every one of the internal nodes. And last day we talked about how we can modify our binary search tree to store internally with it, like an attribute or an instance variable, its height. So we can do this by just having a nice simple way of updating the height whenever we need to. So I want to talk first about a couple properties that AVL trees have. Sorry, I'm getting very excited about this. We're going to talk about a couple properties that AVL trees have, and then we're going to start seeing how exactly we can craft AVL trees out of our binary search trees. So the first thing, and this is really what's going to help motivate why we might want to develop or come up with these so-called AVL trees, is the first property is that any subtree of an AVL tree is also an AVL tree. You could quickly and easily establish this fact by the definition of an AVL tree. So remember, like I said, at every one of the internal nodes, it has to be that the height balance property is satisfied. So if I give you any one subtree of an AVL tree, all of the nodes in that subtree that are the internal ones have to satisfy the height balance property. So it's just essentially just a given, because it has to be holding for all the nodes. That includes that subtree. So I want to first start off by proving a claim for you, because remember, all of our operations for the binary search tree all seem to stem and are built around this whole fact that our time complexities for like put, remove, and get, all of them take big O of the height. So what I want to first do is establish for you that the AVL tree, if I can guarantee you that my binary search tree is an AVL tree, I can guarantee you that the height is going to be logarithmic. So that's what we're going to prove here, is that the height of an AVL tree is at most 2 times log base 2 of n plus 2. I must stress that you can actually prove that it's actually much sharper than this. It's actually quite a bit closer to just log base 2 of n. It's about 1.44-ish times log base 2 of n, I think with a plus 1. I can't remember off the top of my head. The point is that this bound is loose, but it's good enough. Because remember, I want to establish that the height is big O of log n, which I can establish by I could actually prove that that is big O of log n. So let's start off with trying to walk through this proof. Now, I'm going to use a property of binary trees, in particular proper binary trees that we talked about the other lecture. So you're going to see I'm going to bring together a lot of things that we talked about in previous lectures to make this proof work. So the first thing, I'm going to denote h as the height of the AVL tree, t. And I'm going to say that t is a proper binary tree, right? That's what it is, because it's a binary search tree. So we know that the height can be no more than the number of internal nodes. This is a property that all proper binary search trees, or even proper binary trees, have. So this is just a property that we know about proper binary trees. So next, I'm going to use this fact to try to count up how many internal nodes are possible in an AVL tree of a given height. So if I can figure out what the minimum number of internal nodes there are at a given height for an AVL tree, then this serves as an upper bound on what the height is. So please, when you're thinking about this, keep it in the back of your mind. Like if you're wearing a pretty cool hat, put that feather in the back of the cap, hang on to that, because that's what we're going to use. I sound like I'm just about like a Dr. Seuss author at the book at this time. Anyways, what I'm going to do is I'm going to denote n of h is this going to be the minimum number of internal nodes in an AVL tree of height h. So I want to show you some pictures of what these would look like, and we're going to try to figure out what's going on with n of h. So what do I mean by the minimum number of internal nodes? So I'm going to craft an AVL tree that has the smallest number of internal nodes that are possible for that given height. So for example, if I have a binary search tree that's AVL of height 0, it will simply just be a leaf node like this. So you know that there are no internal nodes here, it's just a leaf node, right? If I consider the n of 1, this would just simply be for the AVL tree with the minimum number of internal nodes of height 1, which it's really straightforward to see that this is the one that you need. So notice here that this is the case because I have an AVL tree of height 1. Simply having one internal node suffices to do this. I can't have any less, otherwise I'm going to end up with just weirdly just leaf nodes and they don't connect to anything. I need at least one ancestor to make this work. That's why. So that's why n of 1 is 1. N of 2 is 2. So notice that I could effectively build n of 2 by effectively taking what I had for n of 1. I'm just going to put that right here. I'm just going to copy this, put it right there. And because I need to have a node that has two ancestors, I need to make sure one of these leaf nodes has two ancestors. I want to make sure that I include another internal node so I'm able to achieve this. And all I'm going to do is, I'm not going to worry so much about having any other nodes because I'm just going to put a leaf node there because I want to keep and have as few internal nodes as possible. So in this case, I have n of 2 is 2. So what about n of 3? Let's think about n of 3. Well, this is rather interesting. Let's try n of 3. N of 3, well, I'm going to start off with this because I know that that works pretty well, right? So that I know that works for if I have an AVL tree of height 2. So I'm going to just first start off with that. Now I need to make sure that one of the leaf nodes has exactly 3 ancestors. So I'm going to introduce another internal node to achieve this. Now, I have a bit of a fun question for you. Can I just put a leaf node right here? Yes or no? So I see some yeses, I see some no's. Now, let's think about it. Is this an AVL tree? So let's think about it. If I look at this one node, yes, somebody pointed this out, is that it's because, remember, an AVL tree is a binary search tree that satisfies the height balance property. So you can look at these two nodes and you can see they satisfy the height balance property. So we know that the differences between these is no more than 1. However, this one, it is not true. Notice that the height of this node is 0. The height of this one is 2, right? That's more than 1. So we cannot do that. So I have another suggestion. Why don't I use what I did over there for n of 1? So I'm just going to, instead of doing that, I'm just going to introduce another internal node because I need to make sure that they don't differ by more than 1. And in this case, I can guarantee you that now their heights don't differ by more than 1. Does everybody see that? So these are all AVL trees so up to this point, but I'm trying to minimize the number of internal nodes. So notice in this case, I have n of 3. The number of internal nodes in this case is 4. So naturally, you might ask, Dan, what is n of 4? Does anybody have any ideas what n of 4 might be? Any ideas at all? Does anybody see anything interesting going on as I do this? I will tell you there is no coincidences here. There's no coinky-dinks. So somebody is suggesting 7, and that is exactly it. That is it. It's 7. That's a very good, very good, very good. So let's draw out what that tree would look like. So I'm going to draw out, I'll start it right at the root. And I'll just draw it out. And then if you didn't catch this, I'm going to show you what's going on. So I'm just going to draw out this tree. You'll notice it's very similar to the other one I had. So I'm just going to do the same process. You can imagine I started off with that one. And then I add another ancestor. Then I do something quite similar to what I did in the previous step. So notice that this node has height 0, this node has height 1, this node has height 2, this node has height 3, and this node has height 4. Does anybody see anything interesting going on? So I must stress that all of these are AVL trees, every single one of them. The only thing I haven't done is labeled keys or anything. So you can easily just ensure that it imposes the binary search tree property in the most trivial way possible. I'm just focusing on the height balance property at the moment. So why is n of 3 4? 1, 2, 3, 4. There's 4 internal nodes. Yes, it does. Yes, it has to satisfy the height property. So the height balance property, to be a bit more precise here. So it has to satisfy the height balance property. So notice here that I have height 1, height 2. So this node is okay because it's left subtree and it's right subtree. Their heights don't differ by more than 1. So let's think about this. So I want you to notice something that's really interesting going on here. I'll start with over here, this one I just did here. So I'm going to just draw you a fun little picture, and I'm going to see if we see the idea going on here. So I'm going to kind of highlight parts of this tree. And you can see if there's something recursive about this. Well, that's rather interesting. If you look at the parts that are in blue, say in this picture here, notice that that is n of 0, right? So this would be what would be the tree for n of 0, right? Then this right here is the tree that I had for n of 1. This right here is the tree I had for n of 1. This is the AVL tree I had for n of 2. This right here is the AVL tree for n of 3. Sorry, n of 2. We're 2. I'm getting ahead of myself. I don't want to spoil the surprise. And this is the one for n of 3. So, there's something interesting going on here. Notice that I'm almost effectively building a construction for the AVL trees for each successive value of h, where h is the height here. So notice every time I take whatever, so if I'm looking at, for example, n of 4, well, the value it has is just what its previous value would have been, plus the one that's 2 steps back. So one natural thing is that somebody's asking what n of 5 would be. Does anybody have any ideas what n of 5 would be? So let's think about this. So if I were to do the same process again, I would have n of 3 plus n of 4 plus what? Plus what? So notice each time I have to include the extra internal node, right? Plus 1, exactly. So if I wanted to figure out what n of 5 is, notice n of 5 is just simply n of 4 plus n of 3 plus 1. So n of 4 is 7. N of 3 is 4. And I have the extra 1. So let's see, we got 10, 11. I think this should be 12, right? So I encourage you to draw out what exactly the AVL tree would be for when the height is 5. But you can actually prove that this is in fact the pattern that is actually underlying this whole thing. It's recursive. Is that interesting? So naturally, I would like to write this out as a general recurrence relation for us so that we can actually try to prove something about n of h. And remember, at the end of the day, just remember, keep this in mind in our proof, that n of h relates to the minimum number of internal nodes for an AVL tree of height h. So keep in mind that this will bound from above h. So just please keep that in mind. It's one of the slick things that are in here. It's a very subtle step, but it's an important one. So, fortunately for us, I've written out the relationship that I just described just a moment ago. So I'm just going to take the previous AVL tree's height value, -1. Then I do the same thing with -2. And then I add 1 to it. And I could do this for any h greater or equal to 3. So I can actually do this most generally. So I could have n of h is equal to n of h minus 2 plus n of h minus 1 plus, yeah, with our plus 1, right? Sorry, I'm getting very excited when I see this kind of structure popping up. The great thing about trees is they have this nice inherent recursive structure to them. So sometimes you can find out relationships where one tree helps you build another tree. Isn't that fascinating? So one thing I want to point out to you is that n of h, because every single time it adds 1, you'll notice that this is actually, if you write out as a function, n of h, and you lay out all their values, this is actually a strictly increasing function. So if we think about this, what I actually have going on here is something rather neat. Well, I can bound n of h minus 1 from below with n of h minus 2. So what I'm going to try to do is I'm going to try to come up with a way I can bound n of h in a useful way so that I can relate each part of n of h eventually to some point where I'm going to try to get something related to the height. So we're going to do something a little slick here, so please just follow carefully. So please don't let me get away with anything. So I have n of h. I know that because of the definition of n of h, and I told you that n of h minus 1 is strictly larger than n of h minus 2, I can clearly state that, okay, n of h has to be greater than n of h minus 2 plus n of h minus 2. That's just 2 times n of h minus 2, which, if you actually write out what the definition of n of h minus 2 is, well, this has to be strictly greater than 2 times, so I'm just going to substitute in what this is. This is n of h minus 3 plus n of h minus 4. Now, here's the thing. Here's the slick thing here, is I could do the exact same trick again. I could do the exact same thing I know because, remember, each one of these, I know that n of h is a strictly increasing function, so I can just simply do the exact same thing I just did with this. So I know that if I were to consider n of h minus 4, I know n of h minus 4 has to be less than n of h minus 3. So I'm going to have so I can say that this, what I have right here, is in fact going to be strictly greater than 2 times n of h minus 4 plus n of h minus 4. But that means it's 2 times n of h minus 4. So that means that this is all going to be less than 4 times n of h minus 4. And I could use the exact same trick again. So I'm doing some very slick stuff with the inequalities here, but remember, all I'm doing is I'm just substituting in what the definition is, and I take the smaller of the two as both of them. So that's all I'm doing here. But this, I can do the exact same trick I just described. So you'll notice every time it's just going to multiply out this by another factor of 2. But it's always going to go down by 2 each time. Just like what I did in the previous step. So I can keep doing this over and over again, but notice that it's going up by powers of 2. 2, 4, 8, 16, 32, 64, 128, 256, etc., etc., etc. So I would end up with 2 to the power of I at some point. At some point, I'm going to have 2 to the power of I times h minus, well, I want you to think about this. When I did this process, notice that it's 4 here, and then notice that whenever I do this each time, I'm always removing off 2 each time. So every time I go and I introduce a multiplication, I'm actually subtracting by 2 inside of here each time. Just like here, when I substituted in for h minus 1, I put it h minus 2. Notice that I have 2 of these, but each time I do this substitution trick over and over again, I'm just going to subtract off 2 each time. So when I eventually get to some point like this for an arbitrary I, when I get to the ith power of this, because this is 2 squared, that's 2 cubed, so it's 3 times I, if I think of I like an arbitrary term. So, actually, sorry, it'll be 2, sorry, it's 2 times 2, 2 times 3, and that means that this will be 2 times I, because this tells me how many times I'm applying my trick over and over again. So now you might ask, Dan, what am I going to do with this? So like I said, this is going to be a little slick. So that is n of h is strictly bigger than, I'm sort of writing a little crooked here, is strictly greater than 2 to the power of I of n, 2 to the power of I times n of h minus 2i for any integer I, such that the following is true. Now, you remember that I'll have some process where eventually whatever's inside of that input for that function, you notice I have n of a something. I know eventually it's going to go down to something like n of 1, for example. So suppose I try that. Let's try that. Such that h minus 2i, that's what's in here. I would like to have this where I know that this is at most 1. When it is 1, we know what value it has, and it's in fact 1. So we might say, okay, so what's going on with all of this stuff? What I'm going to do is I'm going to try picking I in a specific way. Pick I such that h minus 2i is either 1 or 2. You might ask, Dad, why am I doing that? So remember, n of h, that is the minimum number of internal nodes that an AVL tree of height h can have. So that's what we were deriving over here when we were drawing out the AVL trees. We were trying to figure out what the pattern was. So remember, just don't lose your eye on the prize. I'm trying to find a relationship between h and n of h. So you might ask, Dan, why am I doing this? It's because I know what happens when I consider n of 1 and n of 2. So I'm going to pick. So let's try picking I is equal to the ceiling. So I'm just going to round up whatever this is for h of over 2. So the ceiling of h over 2 minus 1. Then I'm going to do the following. Then for h greater or equal to 3, I'm going to proceed as follows. So I'm going to do the rest over here on this board. But are there any questions up to this point? I'm setting up something I'm going to do some fun little bit of algebra right about here. So if you're not quite sure why I'm picking I to be like this, I'm going to reveal that shortly. So if we're okay, actually give me 2 thumbs up if we're doing okay so far. So if you're following this perfectly fine, you're doing really good. You're doing really good. That's very slick. So can I go over it one more time? So I have the definition for n of h that I gave here. You can prove that this is indeed the case for the AVL trees. And then what I'm doing is I'm just simply replacing each one of those, see those n of h minus 1s there? Well, I can replace each one of those with n of h minus 2, and that makes the value of n of h smaller. And I can in fact just straight up ignore that plus 1 if I would like to, and it makes it even smaller. So I'm using the fact that we know that functions like this are strictly increasing. So if ever I put in an input, if I put a smaller input in, then I know whatever the outcome of the function is always going to be smaller. That's all it's really saying. Should it be h over 2 minus 1 half? H over 2 minus 1 half. Well, remember, I want to make sure it's an integer when I pick I here. So what I'm going to do is I'm going to try to pick I in an appropriate way so that when I get through this entire process, we're going to see that I'm going to eventually get something that will bound nicely what's going on here. So just watch, I haven't got to the trick yet. So I'm just sort of setting this up. So I like to usually show this proof because it's a little bit more analytical, but at the same time it uses a lot of properties we have for trees. It's a little crafty. It's a little crafty. That's what I'm saying. But also at the same time I want to convince you that the AVL tree indeed has a logarithmic height. So then for h is greater or equal to 3, what I'm going to do is apply the relationship I just established here. So I know that n of h is strictly larger than 2 to the power of h over 2, the ceiling, minus 1, times n of h minus 2 times, and I'm just going to plug right in the ceiling of h over 2 minus 1 to get 2 times the ceiling of h over 2, the ceiling, plus 2, which this, if you look carefully at it, I'm going to want to make sure, because remember, every time if I just keep doing this trick I have over here, if I have what I have right here, it's going to be h minus something that's roughly almost what I need. So I know whatever I'm going to have here, if I were to suddenly put in something that will get it to either be 2 or 1, I'm just going to then just go with 1, because it's always smaller, right? Because remember, n of h is a strictly increasing function. So I'm just going to replace, so I'm just going to leave this like I had before. I'm just going to put n of 1 right here, which n of 1 is equal to 1, right? Yeah, don't worry, I'm not going to ask you to derive this on your own. I'm just showing it to you because it's very important that I want to make sure that you see how you can prove this. This is one of several different ways you can prove this. So I have 2 to the power of h over 2, the ceiling, minus 1 times n of 1. But this is just 1, right? So that means that this is going to be, now remember that this is just the ceiling, right? That means whatever's in the exponent, if it rounds up, will make the number here bigger, right? So that means that I could just simply get rid of the ceiling like this. I can have 2 to the power of h over 2 minus 1. Because it only leads to a number getting smaller or it's the same. Let me just rewrite that h. That h is sort of not happy. There we go. So now what are we going to do here? Well, I'm going to pull out one of my favorite tricks. It's not really mine to say. It's a very helpful one. Is notice that over here I have n of h, and over here I have 2 to the power of h minus 1, all in the exponent there. I would like to get it so that h and n of h relate to each other. Does anybody have any ideas? I'll give you a tip. I would like to make it so that I have something that says h on it in front of something so that I can relate it to n of h. There's something yeah, logarithms. I'm going to take logarithms to both sides. So I'm going to take logarithms to both sides. So let's take logarithms to both sides to obtain the following. So let's see what happens. So I end up with log base 2 of n of h, which this is strictly larger than 2 to the, so it would be log base 2 of 2 to the power of h over 2 minus 1. And now it's 2 to the something in a logarithm of base 2. So I could just use the power rule or power law of logarithms. I could drop that h over 2 minus 1 out front, and I end up with log base 2 of 2, which is what, everybody? What's log base 2 of 2? What is log base 2 of 2, everybody? 1, exactly. So I could just simply write this. So now we're in business, because now I have h here. I got a log with something with this right here, like I promised you. And now, therefore, I'm just going to arrange this in a nice bow. Therefore, h is less than. So I'm just going to simply multiply by 2 on both sides of this inequality. Then I'm going to move this plus 2 that would come as a result over to, sorry, this minus 2 is going to become a plus 2 by adding 2 to both sides. And now I end up with the following. 2 times log base 2 of n of h plus 2. And I have a very simple question for you. Can there be more internal nodes than nodes in the overall tree? So if I have all my internal nodes, yeah, exactly. It can never be more than all the nodes in the tree, right? So if I have this right here, I could just simply say, well, n of h has to be no more than n, right? Because surely what n here is, that will be sufficient. And we're done. We're done. So now I've established to you that the height of an AVL tree is at most log base 2 of n times 2 plus 2. And the big thing for us is that means as long as I can maintain that my binary search tree is AVL, that the height will always be big O of log n. That means that all the operations we've been talking about the last while all run in big O of log n. With one simple sweep, this one theorem, if we can make sure that we have an AVL tree, all of our operations take log n. Is that sweet? Give me a thumbs up if that's sweet. That sounds pretty awesome, right? We haven't had a data structure that's able to do that yet. So now that brings us to how we're going to achieve this. Look, excellent. I'm seeing some pretty awesome thumbs. So we got to talk about how we're able to achieve this so-called AVL tree. So we know how we can do things with binary search trees, right? You're going to see that all I need to do is consider what happens when the tree changes its structure. That namely happens when I do insertions and removals. So I'm going to have to determine how exactly I'm going to achieve this. So that brings me to talking about so-called rebalancing operations. So I told you that the AVL tree is a self-balancing tree. That means that every time I make a change to the tree, as in I do an insertion or removal, it's going to self-adjust itself so that the heights all are maintained to satisfy the height balance property. So it means every time I do an insertion or removal, we're going to ensure that if I make any oopsie in the modification of the tree, I can ensure you that the tree is capable of detecting this and fixing it, which is quite slick if you think of it like that. So let's talk about rebalancing, which is going to be the key part in this whole process. Rebalancing AVL trees. So let's talk about rebalancing AVL trees. So the first thing I need to point out to you, as I mentioned just a moment ago, AVL trees will inherit. You can both say this figuratively and literally. If you're thinking more of an OO kind of way, it will inherit the operations of a BST. So as I mentioned, the AVL tree will rebalance on put and remove operations. So anything we're trying to do insertions and removals on the tree, the AVL tree is going to do that rebalancing process. So what exactly is the rebalancing going to do? It's going to do the following. To rebalance an AVL tree will rebalance the smallest unbalanced subtree. So do you remember the first property I told you is that any subtree of an AVL tree is also AVL, right? So it means that if an imbalance happens that violates the height balance property, because remember, our goal is that before we do an operation like an insertion or removal, the height balance property has to be true at every internal node. And then after I do one of these operations, it has to be that the height balance property is maintained over all of the internal nodes. So just keep that in mind. It's very important. Otherwise, we're going to destroy the structure of the AVL tree. So we're going to make sure if this happens, the way that the rebalancing is, sorry, I'm getting very excited here. The rebalancings will occur at the smallest unbalanced subtree. Why? If I make a correction in that subtree, such that it's AVL, then the entire tree has to be AVL still. That's the big thing I want you to notice. So this plays a very big role in how we actually rebalance the tree. So how to rebalance relies on the idea of a simple rotation. So often it's just called a rotation, but I'll refer to it as a simple rotation because we're going to have a couple other variants of the idea of a rotation. So rotations shift around the heights. So when I talk about the heights, I'm talking about the nodes specifically. The heights by rearranging the nodes while maintaining the order of the tree's elements. Can somebody tell me why it's really important that we maintain the ordering of So a quick question, every time we perform an operation, we should check whether it will satisfy the property of AVL tree? Correct. So what's going to happen is as I make modifications to the tree, there's going to be a very specific point I can check in the tree, and I could work my way back up the tree towards its root and determine the smallest subtree that becomes unbalanced. And what we're going to do is we're going to be doing these rebalancing operations through these so-called rotations to fix that smallest subtree. And if we could do this, we can ensure that the whole tree is rebalanced. So good to go. So I want to talk about this rotation business. So remember, the order of the elements is very important. If I violate the binary search tree property, is it still a binary search tree, everybody? No, right? That's another thing in play. So you know how I talked about the height balance property? We need to also make sure that the binary search tree property isn't violated either, right? So just like when I did my insertions and removals with the binary search tree, I have to make sure that that also is the case if I make any changes to what the tree looks like, its structure, its shape. So let me just erase this. I'm going to draw some fun pictures. One thing I'll tell you up front is that I'm going to draw you a lot of fun pictures, and I assure you that while they look simple, they're going to play a key role in how you might actually implement an AVL tree. So what I draw here is going to be a rather simple version of what you might actually implement. So you have to think about things like parent references, like the pointers to the parents, their children, and making sure those are updated appropriately. All of them are going to be pointer adjustments. So I'm going to draw a fun picture of what one of these rotations looks like. So this is what a simple rotation will look like. So I'm going to draw a fun picture. I must stress that it may not necessarily have a parent, but I'm going to draw it as a dashed line here to keep things simple. So I'm going to draw the subtrees as triangles here. So this would be a subtree, that's a subtree, and this is a subtree. Then I'm going to draw another one on this side. It will show us what the result of a rotation will be. And I'm going to explain this very carefully, because it's kind of the key part of the AVL tree. Got a lot of excitement here. So with that being said, I'm going to tell you what we're going to talk about this rotation operation. So there's going to be this idea of a right rotate or right rotation. I'll refer to it as right rotate. And then we're going to have this idea of what we call a left rotate. And the way I would denote these to you as operations is that the right rotate is a rotation on X. So it's going to be rotate X. The left rotation in my picture is rotate Y. So you might ask, Dan, what is this all about? So question, is recompute height from the previous day related to rebalancing AVL trees? Exactly, it is. So what's going to happen is we're going to make adjustments of this tree. And as we make these adjustments, we're going to sometimes have to update the heights of the nodes because we're going to rearrange them. So I want to talk about the idea of a rotation. So the first thing I like to really kind of do, I need a cat. I need a cat. Where's a cat? I need a cat. I need a cat. Give me a cat. I need this cat. Okay, I got a cat. I got a cat. So this is Miss Kitty. Everybody say hi to Miss Kitty. So Miss Kitty's going to help me talk about what a rotation is. So in a rotation, I have a node, and I would like to promote the node and demote the parent. So if I'm the parent and I want to rotate Miss Kitty, I would promote Miss Kitty and I would demote myself. Do a voice for Miss Kitty. Hey guys, it's me, Miss Kitty. Huh. But this is what's going to happen with Miss Kitty, just like my node X. So when I do a rotate on X, what's going to happen is I'm going to promote X and I'm going to demote y. I'm the parent now. That's what's going to happen. And the way I like to think about this is very much like if I had a hanger. So I imagine I had this hanger and I had a string that runs across this hanger. What I would like to have happen is I would like to pull up x and bring down y. So imagine I pull the string up like this, and this will bring up x and it pulls down y. So when this happens, however, one of the sides might be potentially a little heavier. So I want to imagine it like I have a weight right here that I'm going to pull over onto this side. Intuitively speaking, it doesn't necessarily affect the height itself, but there's an intuition that if I have a really lopsided tree, I would like to drag some parts of that tree over to the other side to potentially rebalance it. So this so-called rotate operation is actually reversible. So I want to do an in-order traversal of this tree and then an in-order traversal of this tree. Just so that I could convince you that rotations preserve the ordering of the tree. So if I imagine I have all my keys in the internal nodes here, the in-order traversal of this tree, let me just grab a different marker. The in-order traversal of this tree is T1, X. So I would go all the way down to the left. Whatever's in here, I do the in-order traversal. That's going to be what T1 is. I visit X. Then I visit all of the keys in T2. Then I visit Y. Then I consider my right subtree here. So if I actually did an in-order traversal of this tree, this is what it would look like. So keep in mind that those subtrees there, they may contain many, many nodes that may have records in them. If I look at the in-order traversal of the right tree, what I want you to notice is if I do the in-order traversal, I would go left, I visit all the keys in T1, then I visit X, then I go to my right, but I go left first, then I visit myself, then I go to my right. Are these in-order traversals any different? Are they the exact same? They're the exact same, right? So this rotate operation actually preserves the ordering of the tree. So all of the nodes in my tree, when I look at the keys, if I do a rotate operation, if I go rotate X or rotate Y, I do a right rotate, left rotate, however you'd like to imagine it. Like if I'm dragging one direction this way or one direction this way. They're symmetric, by the way. If I do this, you know that it will never violate the binary search tree property. That's the big takeaway if I do this operation. So at the heart of how we're going to correct the tree is going to be these so-called rotate operations. So you might ask, Dan, how efficiently can you do one of these rotate operations? So you might ask, Dan, what the heck is going on with this rotate operation? So if you're looking at this and you're like, okay, well, how the heck do I do this? So remember that I want to promote X, so I want this to go up and I want Y to come down. But remember what's actually happening, and keep in mind that there is a symmetric case of this that looks just like that one, except it's Y, it would be X over there and Y would be up here, is I would like to make Y's parent be X, just like when I took Miss Kitty and I promoted Miss Kitty. But notice that when I do this rotation, where T2 is. So just take note of where T2 is. T2 moves from one side of the subtree, it's one side of the tree to the other side. It sort of gets hung around to the other side. So just very, very much don't forget about T2. So T2 is something you got to keep an eye out for. You'll know very quickly because you may have an ambiguous notion of what the right child or the left child is of a node if you don't know where T2 is. So anyways, let's talk about what you could do with this. So first, all I told you about rotate is that it just rearranges the nodes so it updates their left child, right child parents. of these two nodes, and obviously you might have to check these nodes and make sure that you update their parents appropriately. So when I do this, all I'm doing is a constant number of pointer adjustments, right? That's all that's happening. So if you're looking at the time complexity of one of these operations, so all it is a constant number of pointer adjustments. So you just update the left, right, and the parents appropriately. And this takes big ol' 1 time. So it's constant time. So remember, this is just how we define the rotate operation. That's how it's defined. So this is what it does. So notice that it just maintains the in order for all of our keys. So that's good enough for us, right? But it has some nice, lovely properties. So now, there's really actually 4 kinds of rotations that do exist for the AVL tree. They're all based on the rotate operation I just drew here. So if you could think about these operations I'm going to show you in terms of this rotate operation, as soon as you could do that, all of them are really easy to describe. They're just symmetric cases of each other half the time. So there's 2 kinds of rotation. So this is a simple rotation, which I've referred to as rotate of a node. So there's only 2 kinds of main rotations that happen with an AVL tree. So there are 2 kinds of rotations. So this means that there's 4 in total. Single rotations. So for example, our simple rotation is an example of a single rotation, but we have a very specific case we're going to be looking at with the AVL tree. So single rotations and so-called double rotations. So I must stress that I will expect you to know how to perform these operations. So keep in mind, we will see examples of doing this. So let's head over where I am. I'm way over here. Hi, guys. I'm over here. Let's go over here. Come on. So let's talk about these rotations. So the first kind are the single rotations. So you might ask, Dan, what the heck is a single rotation? So I'm going to describe them by drawing pictures to you. And once you understand what it is, it really becomes actually very much an idea of just understanding what rotate is. So the first kind are single rotations. So our single rotations, these are known as LL rotations. So an LL rotation and RR rotation. So what are they? They're just going to be a single left or right, respectively, left, right. I'll make sure I note this, respective. Rotate, a single left or right rotate from the tallest child of an imbalanced node. So you might ask, what is that all about? So let's take a look, and I'm going to draw some fun pictures. So remember, all of these are just pointer adjustments. So all I'm doing is updating the left, right parent. And then I might have to recompute the heights of certain nodes. Remember, it's just a constant number of them that are changing every single time. So I'm going to first draw our first one. So it's going to be a node called Z. I'm going to have another one called Y and another one called X. So I'm going to have 4 subtrees, T0, T1, T2, and T3. And what I'm going to do is I'm going to perform a rotation at a specific node. So suppose that Z is the one that is imbalanced. So suppose Z is the imbalanced node. What I want to do is I want to determine which of my 2 children is the taller of the 2. Taller meaning that it has a larger height. So in this case, it is that Y is on the right, and it is the case that if I look at the structure of this, I'm going to have it where if I look at the structure of this, if I look at its children, then I look at the next child that is the taller of the 2. You're going to see that I'm going to give you how to detect these, by the way. So if you're wondering, Dan, how do I know when to apply this? Don't worry, I will tell you in a little bit. If not today, we'll talk about it on Tuesday. So I'm just drawing you some pictures of what these rotations actually look like. So if I have, so my RR rotation will look like this. So what it's going to do is it's going to provide or do a rotate on Y. So it's just going to do rotate on Y. So that means it's going to promote. Remember, think of Miss Kitty going up into the sky as I fall down into my doom. Just like the string getting pulled on the hanger. Y is coming up. That means Z gets demoted. And that means that I'm dragging X along with me. So what will happen is I end up with my subtrees looking like this. So this is what the RR rotation would do. So just remember that Z might, for example, have a parent. So be very mindful of this fact. This is something that sometimes students forget, or just generally when you're implementing AVL trees, people forget about. And what happens usually in these kind of cases, at least testing-wise, is you'll have it where a part of your tree just sort of just disappears and you wonder where it goes. Oftentimes, because the rotation, you fail to update the parent, so when it was working its way up, it sort of just doesn't know where to go after that. So that being said, that's the RR rotation. So all it does is just do rotate on Y, so it promotes Y and it drags, so it means it demotes Z. And that means everything else that comes up with Y, like X, will come up with it, and I'm going to have to trade over T1. So T1 is going to go over to hang out with Z. So think of it like playing hot potato. I'm just moving it on over. So the other type is the LL rotation. It is the symmetric case to this one. So I have Z, Y, and X. It's very exciting over here. It's like a party. So I have T0, T1, T2, T3. And the same idea, I'm just going to rotate on Y. So this is an LL rotation. You just rotate on Y. So remember, think of Miss Kitty. Miss Kitty is going up, I'm going down, okay? So that means that Z comes down, I go up. Sorry, Miss Kitty goes up, I go down. Tough luck for me today. So that means that Y goes up. Then I have X on the left. Z on the right. Then I have my 4 subtrees, T0, T1, T2, and T3. So notice here, because this it is just performing a rotate operation, it preserves the binary search tree property. And the other thing that I haven't quite got to is exactly how this corrects balancing of heights, which I haven't yet talked about really quite yet, which we'll see when we actually get into the juicy bits of how we actually use these rotations. So let's talk about the other two. So the one thing I usually recommend to students, if you really just don't like seeing these fully played out, just remember where the rotate has to happen. If you remember that, it's a piece of cake. So now we have our other two rotations. We have the double rotations. As the name suggests, that means that we're going to do two rotate operations. Next, double rotations occur when the tallest descendants of an imbalanced node form a so-called, some people call it this, there's another data structure that does use this jargon. For example, in CS 340, we usually talk about splay trees, for example. They specifically use this discussion of a notion of a zigzag. Form a zigzag pattern. These are RL rotations and LR rotations. So what do we do to resolve it? To resolve the imbalanced node, apply a simple rotation, i.e. a left or a right rotate, appropriately twice to the tallest grandchild. So tallest is in the same notion as talking about what I talked about over there. It's just the tallest of, so if I take the taller of the children, then I take the taller of those children, that's the tallest grandchild. So let's draw some fun pictures. So naturally you might ask, what do you mean by a zigzag pattern? So you'll notice that in my first two types of rotations, for my single rotations, my first of the four, likewise the second one, notice that they both go left, left, then they go right, right. That's where the names of these rotations come from. It's the direction that the descendants go in. So it forms two in the same direction, or it's going to be that it goes one direction, then the other direction, hence why we say zigzag. So let me draw this out. So I'm going to have Z, Y, and X. So I have T0, T1, T2, and T3. So the first thing I want to point out is that if an imbalance occurs at this one, that means that somewhere in this tree there had to have been some imbalance, right? So the question is, if it looks like this pattern, where does it happen? It will possibly happen down here. Now, I don't have time to prove it to you, but the double rotation will be nice for correcting imbalances in a nice, much more definitive way. It's a much more powerful way of fixing the heights of nodes in a tree. So if I do the RL rotation, as I said, I'm going to take the tallest grandchild. So this is the taller of the two children. And then I take the taller of this node Y's children, which is X. So all a double rotation will be is I just do rotate X, then I do rotate X. So I just do rotate X twice. That's all it is. So if I do this, what happens? If you walk yourself through this process, you'll have X at the top here. Then you'll have Z. Then you have Y. And then you'll end up with T0, T1, T2, and T3. So one thing I do want to mention from an implementation standpoint is that you could quite literally just hard code each one of these rotations and literally do all the pointer adjustments as I show in this picture. You can conceivably do this, or you can even just simply just implement the rotate operation and then just in the appropriate case for what rotation you use, you just apply a double rotation or a single rotation, and the determining of if it's an RL or an LR rotation. As you see, I always seem to have these three nodes, these tri-nodes, so three of them that tend to determine which rotation I'm going to end up using there. Why did I choose X there? It's because this is the specific node I have to rotate to fix the potential imbalance. So, as I mentioned, double rotations are effective at fixing heights of nodes, specifically in a much stronger way. So single rotations can do it, but a double rotation guarantees it. So we're going to see this actually in a couple of our cases probably next time. So this is what an RL rotation is. The LR rotation is just symmetric to this one. So I'm going to just draw it over here. So let's see what happens. So if somebody's asking, how do I know that I have to pick that particular X? So as I mentioned, what's going to happen is that you're going to be detecting where the Z, Y, and X line up. So does it go right and then left? Does it go right and then right again? Does it go left and left? Does it go left and right? This is actually the way you easily can detect which rotation to use. So either a single rotation or a double rotation. So whether it's LL, think once, then twice, right, right, or it'll be right, left like this. We'll see when we actually get to the algorithms how this plays out. So here's the LR rotation. So it's just symmetric to the other one. So you know you're going to be rotating an X. So I have T0, I have T1, T2, and T3. And I'm going to do my LR rotation. So remember, double rotations, we're just doing rotate X twice. That's all it is. Don't make it more complicated than it has to be. If you're not convinced by the picture, just simply think of Miss Kitty getting promoted and I go down into that hole. I get doomed. I'm getting demoted. Just think of it like the string pulling up those nodes, and I grab that T2 like I had originally in my rotation picture and just hang it over to the other side. So in this case, we'll have Y on this side, we'll have Z on this side. And then I have T0, T1, T2, and T3. So one thing I want you to notice is that the rotates, like I mentioned about my string with my hanger. So if I find it there's an imbalance, the intuition behind this is that if I have deeper nodes on this side, I want to drag them up by pulling them up this way using the rotation, just like it's being pulled along on a string this way. That's the idea behind the rotation. So if you find yourself like, okay, so what do you mean by this? Has anybody ever heard of the game, The Floor is Lava? Like, you may have played this as a kid or something like this. So you can imagine it like imagine you have the lava here. Imagine you have the lava, and you're like, hey, look, I want to make sure that if I see something really close to that lava down there, I want to pull it up. So what I would like to do is do these rotations to pull up one side of this tree, and then hopefully balance it out. By pulling it up, you're reducing the height of a node. That's the thing I want you to notice, is that when I make this modification through a rotate operation, by promoting and demoting, I'm changing the heights of nodes when I do this. So if you ever find yourself just not sure about this, just remember, the floor is lava. We don't want to go in the lava. So you might ask, what exactly were you going with this? So I just want to mention, so each single and double rotation, because remember, rotate takes constant time. So each single and double rotation takes constant time. Just be aware of that. That's very important for our algorithms. So you might ask, how do I determine which rotation to apply? So if we end up with an imbalance at Z, so how do we determine which rotation to apply? It's very simple. It's very simple. Let me just switch my marker here. I swear, I don't even know how many markers I even go through with this process. In my 340 class, some student, I don't know if somebody's keeping a tally of these things, but I tend to go through a lot of markers. So which rotation to apply? Well, think of it this way. If an imbalance occurs, I want to know which string do I need to pull up to reduce the height at a given node. So I'm going to try to find out which one's the tallest of my children, or potentially the grandchildren. So let's talk about that. So how do you determine which one to do? All you do is determine the tallest child. So the tallest child Y of the imbalanced node, node Z. So just like in my pictures, I have Z, Y, and X. So first, to determine Y, you pick the taller of the two children it may have. So you just pick the taller of the two. That's what Y is. Then determine the tallest child X of Y. So just read it off as Z, Y, X, like this. So for example, to go from Z to Y to X, if it is where I go left, then I go left, what kind of rotation should I use? What kind of rotation should I use? If Y goes to the left, then X is my left child of Y. So here's the trick. Notice that if I go left, then go left again, it spells out the rotation right here. It's LL, exactly. If it's LR, Well, notice you go left, then right. So you know you're going to use the LR rotation. And each one of these is defined by these rotate operations. So there's actually a way you can easily check which of the two to determine. So all you have to do is figure out which of the two children is always the tallest one. So that's really all it is. So that being said, we're going to stop right here. I would love to just keep going, but when we come back next time, we're going to talk about how we're going to incorporate these rotations into the insertion and removals for the AVL tree, and that'll be basically what's left for the AVL tree section, along with just mentioning a couple of fun things about AVL trees. So that being said, I want to say thank you very much, and have yourself a beautiful day. I'll see you later.